So we started with this problem, right? So this equation we have that has the degree is 4 equation. This polynomial we have,
Uh-huh.
and we have to find how many solutions are there, mod 11,
Yeah. Mm-hmm.
right? So the first aim was to find the roots of the equation, right? So naturally, if we can find out some roots of this equation,
Mm-hmm.
so then just putting x equals to 1, we saw that that satisfies the polynomial, right? The equals to 0.
All right.
So then we want to take out so x minus 1, so since 1 is a solution, so x minus 1 will be a factor of this polynomial, right?
Mm-hmm.
Right. So we take out this x minus 1 factor, and now we have to find this another polynomial gx, such that x minus 1 times this gx will give us the original polynomial, right? So how to do that? So this part, is it clear?
Yes, we were factorizing x minus 1,
Right.
and then we have gx, and then we need to keep factorizing that gx, right?
Yes, yes. So means how we obtain gx, this part is clear, right?
Yeah.
Right. So now we have
Yeah.
to further factorize gx. So any idea? So how to do it? Because it is a cubic equation. So once we have quadratic equation, I know that there is a formula. But still, it is cubic equation. So still I don't know any formula for that. So direct formula we don't have. So can we find out any other route that is easy to see? So for example, one more thing what we can see is. Uh, So here you can see that 6 and 4 is there.
Mm-hmm.
Okay, let me think. So you have minus 1 if I take, I was thinking about minus 1. Okay, just let me check the roots. Yes, so you try, you tell me. So any other factor can we take out from this equation? So minus 1 you have taken. So means x minus 1 you can take out the factor. So any other factor you can do.
Let's see.
So yes, so you have to try some things. Otherwise, there is no other option. The thing is, if I put so here all of the things are positive, right? So
Mm-hmm.
if I put some x value, positive x values, then it will not 0, right? It will not become 0, right?
Right.
So I have to check with some negative values of x, right?
Mm-hmm.
So whether it is working or not. So if I take x equals to minus 1, suppose, so is it working? So then I have minus 1 cube plus 6 into minus 1 square plus 10 into minus 1 plus 4, right?
Mm-hmm.
So this is alternatively it will be this, but this is not equals to 0, right?
No.
This is not what. Now let us check for minus 2. So minus 2 is minus 2 cube plus 6 into minus 2 square, 10 times minus 2 plus 4, right? So
Mm-hmm.
it is minus 8, then it is 24, right?
Mm-hmm.
Minus 20 plus 4. So this is 0, right? Because
Right.
24 and 4 is 28, minus 8 and minus 28. So
Right.
yes. So x equals to minus 2 is a uh,
Nice
solution.
solution. Yeah.
So I can take out a factor of x plus 2, right?
Yeah.
So x cube plus 6x square plus 10x plus 4. So here I can take out a factor of x plus 2. So now we have to do the adjustment. So this is x cube plus 2x square. So the adjustment is 4x square. And here we multiply by 4x. So I get 8x here, and here is 2x plus 4. So it is, sorry, 2 times of x plus 2, right?
Right.
So x plus 2, I can take out a factor. So x square plus 4x plus 2. Right. So suppose this initial equation, let us take for easy f of x. Then what I have is f of x is nothing but x minus 1 x plus 2 times x square plus 4x plus 2. Right. So
Mhm.
now what happens to x square plus 4x plus 2? What are the roots? This we can easily find out, right?
X squared 4x.
So the quadratic formula you know, right?
The quadratic formula? You mean the.
Yes, so there is a formula, right? So for example, so suppose the equation is ax square plus bx
You
plus c
mean
equals to,
the plus minus b plus minus
yes, that one.
square
So
root for b square minus 4ac.
right, so these are the roots. So now here,
Mm-hmm.
from here you can check. So a is 1, b is 4, and c is 2. So it will be minus 4 plus minus 16 minus 4, 4 2s are 8, right?
Yeah.
4a into c and divided by 2. So yes, so it is root over of, after subtracting, it will be root over of 8, right?
Mm-hmm.
So yes, so this is not an integer, right?
No.
So it is, so we don't have to take care of that. So in integers, it does not have any factorization, right? So only two roots that we are care. So only two solutions will be these two things,
Right.
right? So what they are asking is, mm, so what are the, how many solutions are there in modulo 11, right? So there are only two solutions. So one is so so they are saying that are there four solutions or there are fewer than four solutions. So of course there are only two solutions.
I mean, I guess there are at least two.
Yes. So there are only two solutions in modulo 11. So one is 1 and another one is minus 2, or one minus 2 is nothing but 9 in modulo 11, right? So 1 and 9 are the solutions. Fine.
So how did we use the module 11 there? We didn't use it that much.
Modulo, no, no. So modular here we did not use much. So only thing is, yes. So only thing is that here, if you put x equals to 9 in the original equation, then it may not be 0. But once we take modulo 11, that will be 0. So that is the only observation.
Sorry, can you say that again?
Yes,
You
yes. So what
mean
I'm saying is, so here in the original equation, so if I just find the roots in integers, it is 1 and minus 2, right?
uh-huh.
But if I put 9, then the original equation is not actually equals to 0, but it will be 0 in modulo 11. So that is the
Oh,
observation.
I see. Okay.
Fine.
Okay.
Right. So this was part A. Right. So the next part is, so part B is they are saying, so consider the congruence. X square minus 1 is congruent to 0 mod 8. Then how many solutions does it have in modulo 8? Yes. So tell how to do it.
So in the previous exercise, it says x is greater than 0 and less than 11.
Right.
I mean, we didn't use that also.
Yes, tell.
I mean, we didn't use that part, or what was that for?
Yes, that is we used it because we are only finding solutions between 0 and 11. So that is why we got 1 and 9, right? Because minus 2, that's why I converted to 9. Because my range is from 0 to 11.
Okay, okay, I see, I see. Okay,
Okay. So
okay,
now
okay.
for this one, our range is from 0 to 8. Yes. So how
I
many
mean,
solutions are there?
we can just factorize, all right? X minus x plus 1, x minus 1.
Yes, that will be there. So yes, so actually there will be more solutions. Not only those two solutions. So other solution, oh yes, that let us do at least that. So x square minus 1. So this is x minus 1 into x plus 1. So x equals to 1 is a solution and x equals to minus 1 is a solution, but minus 1 is nothing but 7 in modulate, right?
Mm-hmm.
So these two are solutions, that is fine. Any other solution can we have? So actually what is
And
happening is, so the range of x is 0, 1, 2, 3, 4, 5, 6, 7. So we can check actually if anything else is a solution or not. So 0 will not work. 1 is a solution, that is fine. 2 square is 4. 4 minus 1 is 3, so that will also not work. So 3 square is 9, minus 1 is 8. So that will 3 is working, right?
yeah, it works, right?
Yes. 4 will also not work, but 5 will again work because 5 square is 25 minus 1 is 24. And 7 works. So here actually the solution set is, so
There
it
are 4
has,
solutions.
right. So there are 4 solutions, that is 1, 3, 5 and 7. Yes. The thing is, now the next question in that same question only. So they are saying that notice that there are more than 2 solutions that we already observed, but the why does not it contradict the polynomial root mod p theorem? Because what does the theorem says, and why does not it contradict it?
That it does not what?
Yes, so it is saying, right, why does not this contradict the polynomial root mod p theorem?
Mm-hmm.
Yes, what will be the answer? That is the question. So first of all,
Well,
we have to go to the theorem, right? What does the theorem say? The theorem says that the maximum number of root means the number of roots cannot exceed the highest degree, right? That is the theorem saying.
yeah.
So, but here actually you are getting an example where the degree is 2, but you are getting 4 solutions. But there is one more condition. So, why it is not violating the theorem? So, that is the question. So, you understood what I am asking, right?
So you're saying if we have a equation which apparently only has 2 solutions, but when we test it, we have 4 solutions. So why that is not a contradiction?
Yes. So, the thing is, the theorem that we learned, this polynomial root theorem. So, that is saying that the maximum number of solutions, maximum number of incongruent solutions that a polynomial equation can have is the degree of the highest, that is the degree of the polynomial, right?
Okay, it has the maximum number of solutions.
Yes, but here the degree is 2, right? But we are getting 4 solutions.
Mm-hmm.
So but why it is not contradicting the theorem?
Because it's maybe because it's a module. I mean, module will,
No, right? Because these are all incongruent solutions. So here modulo, we have already taken modulo 8, so that is
right.
not a problem.
I don't know. I don't know.
Yes. So actually, if you remember the condition on the theorem, so let me go to the statement once. Yes. So this is the statement. So here is saying that D is the highest degree. So degree greater than equals to one. It has at most D incongruent solutions. So that is the theorem.
Mhm.
But the assumption in the theorem was P need to be a prime number.
Right.
So modulo P when you are taking, if P is a prime number, then only this theorem satisfies. But the problem just we did, that is mod 8, and 8 is not a prime number. So that's why it is not contradicting this theorem. So this theorem is not applicable there,
It's not applicable
right?
because you need a prime number.
Yes, yes. So the statement starts with the condition that P must be a prime,
Okay, okay.
right? So that is the thing. So that's why it is not a problem.
So you're saying P is not a prime, that's why it doesn't contradict the theory.
Yes, yes. So yes. So since 8 is not a prime.
Mhm.
So the theorem is only valid, or the theorem only states the condition when the P is prime. That modulo thing is prime.
Mhm.
Fine.
Yeah, understood.
Okay. So the next one is, so let P and Q be distinct primes. Then what is the maximum possible number of solutions to a congruence of the following form? That is x square minus a is congruent to 0 mod pq. Right. So here also we cannot directly apply the theorem because this multiplication of two primes is no longer a prime, right? So this is a composite number, but this is a special type of number that it is a product of two distinct primes. So can we say something that what is the maximum possible number of solution this congruence will have? So yes. So as usual, we are only interested in distinct modulo PQ solutions, that is incongruent
Mhm.
solutions.
Okay.
Yes. So let us try to see an example what is happening. Then we'll try to see for the general case.
Mhm.
So let us take two small primes. So suppose P is 3 and Q is 5, right? And let us take A to be 1. Then what is our equation? So x square minus A is congruent to 0 mod 15, right?
Mhm.
That is our equation. So now, so that is nothing but x square is equivalent to 1 mod 15. Yes, can you tell what will be the solutions? So this is easy. We can just verify all the terms from 0 to 14. Okay, so can you find the solutions?
Let's see. I mean, we can just root the minus b plus minus root square and so on.
No, I did not get. Tell again.
Since we have a square over there, maybe we can use the
No.
if it
Yes. So the thing is, two solutions we already know, because so from here I have x minus 1 into x plus 1. So x equals to 1 and minus 1 will be a solution. So 1 is 1 and minus 1 is 14 in modulo 15. So this 1 and 14 is also its solution. That is clear. So any more solution do I have? So that is the question. So that you can manually verify. So from 0, 1, 2 up to 13, 14. So yes, so just check and tell me. So 1 and 14 we know. Anything else is there or not? So 2 square is 4, that is not. 3 square is 9, that will not work. 4 square is 16, and 16 is 1 mod 15. So 4 will work, right?
uh,
So anything else? So from here, 4 will work. Anything else? Check the remaining ones.
4 will work. Mm, well, 5 will not work, right?
No, 5 is not. 25 is not 1 mod. 6, 36, that will also not work. Yes.
No.
Then?
I mean, anything that not finishes in 5 or 0 will not work.
Yes, that will not work. Yes.
So maybe 8 will work.
8 is 64. That will not work. 9 is 81. But 80 does not divisible by 15, right?
Mm, sorry,
10
what
will,
did you
10
say?
will also not work, right?
Yeah.
But
Yeah.
11 will work, right? So 11 is 121, and if you subtract 1, it is 120, and 15 divides 120, right?
Yeah.
So 11 will work. And 12, 144 will not work. 13, 169, that will also not work, right? So here you can see the set of solutions is 1, 4, 11, and 14. So
Mm-hmm.
this is the solution set, right?
Mm-hmm.
Fine.
Yeah.
So this is the for this equation I have the solution set as 4 solutions. So I guess from here what you can get is maximum 4 solutions it can have, right? Or at least 4 solutions it will have. We have to prove that that is the maximum number of solutions. So that they are asking, right, what is the maximum number of possible solutions? Okay. So up to this is clear, right?
Hello?
Up to this is clear, right?
Mm, 1 second. So in order to deduce the other solutions, besides the equation, besides the factorization, like
Yes.
1 and minus 1. Okay, but minus 1 is not part of the solution. Maybe it is, right? You can consider, but you can convert the negative to a positive.
Yes. I just converted into 14 because in modulo 15 we are doing it. So minus 1 is equivalent to 14 mod 15.
So the only way to find out the other solutions module PQ is to test, like there is no formula.
Yes. Yes. No, actually, we don't have to find the solutions, right? So they are asking what is the maximum number of solutions possible. So you have to give the number of solutions. We don't have to find the solutions because here it is one. That's why I can do the factorization. But a I don't know, right? So suppose it was three here. Yeah, if a I have taken one, if a was three, then I cannot do this factorization anymore, right?
Yeah.
So yes, so actually we don't have to need to find the solution. We have to find the maximum number of possible solutions. So that is the more important thing.
Okay. Okay. Okay.
Yes.
Okay.
So yes. So maybe we can go by a contradiction. So the thing is, our claim is. Let me write down.
Mhm.
So this is our claim. So it has the maximum number of solutions is 4.
Mhm.
Okay. So we'll try to prove by contradiction. So we'll assume that there are more than 4 solutions and try to arrive at a contradiction. So suppose that R1, R2 up to R5 are 5 distinct solutions.
Mhm.
Right. So distinct solutions means in congruent they are distinct, right?
Yeah. Incongruent.
So distinct solutions to this equation. So x square minus a is 0 modulo pq, right?
Mm-hmm.
Right. Right. So now, so since these are solutions to this equation, so now if I reduce them to mod p, so they are also solutions to. Okay, let me write down. So reducing them to modulo p, so they are also solutions to this equation. X square minus a is congruent to 0 mod p, right?
Mm-hmm.
Is this clear?
Yeah.
Right, because the thing is, from here what I have is that pq divides x square minus a, right?
Mm-hmm.
So this will imply that p also divides x square minus a, right?
Right.
So that's why these solutions will also work for this equation also. If I reduce to modulo p,
Mm-hmm.
right? So for example, if we go back, so these are the solutions of modulo 15. So now if I reduce to modulo 3, then what will be the corresponding set? So this set will reduce to 1. 4 is also 1 mod 3. And 11 is 2 mod 3, right?
Mm-hmm.
And 14 is also, I think, 2 mod 3, right?
Mm-hmm.
Right. So this will be the solution. So you can check here. So here, if I change to 3 here, so 1 square is 1, that is fine. And 2 square is 4, that is also 1. So 1 and 2 are the solution to x square equals to 1 mod 3, right?
Okay.
Right. So that is what we are doing here. So if I reduce these 5 solutions to modulo p, then it will be solutions to this equation.
Mm-hmm.
Right. So now, since p is prime, we can apply the that mod p theorem, right?
Okay.
Right. So since P is a prime by that mod P theorem, so there are at most two solutions. Right?
Most two solutions because of the degree 2 minus 1. We have
Right.
0 and 1.
Yes. The degree is 2, right?
Mm-hmm.
That's why using that theorem, that mod P theorem, it can have at most two solutions, right?
Right.
Right. So suppose it is so these two solutions. So suppose it is S1 and S2, right?
Mm-hmm.
So, but the thing is, there are five integers, right? Or five solutions, and this one has two solutions, S1, S2. So what we can say is, so each of R1 to R5 must be congruent to modulo P to one of S1 or S2, right? Is it fine?
Each of the roots
Right.
must be congruent on the repeat to one of what of the
Yes, it will be congruent to one of S1 or S2, right? That is the condition what we got.
okay.
Fine.
Mm-hmm.
So, what can we say? So, pigeonhole principle, you know?
Which one?
Pigeonhole principle.
I mean, I heard of that.
Yes. So, pigeonhole principle. Okay, I think name actually you don't need. The thing is, if five things is either S1 or S2, so at least three of them should be same, right? Three of them has to go to the same. So let me explain. So suppose there are two boxes, right, and you have five objects. So you are distributing these five objects among these two boxes. So at least one of the box should have three objects, right?
Right.
Yes. So that is the pigeonhole principle. Okay. So these five things R1, R2, R5, they are they are either S1 or S2. So then what we can say is, so it at least three of them. So hence
Mhm.
at least three of the RIs are same in modulo P, right? Fine. So I think up
What
to this is
was
fine. Yes.
what was S1 and S2?
S1 and S2 are two solutions, right? So this equation has two solutions, right? Incongruent solutions.
And
So
R1, R1 to 5, what is?
R1 to R5 is the original solutions. So we are assuming that this equation, that is modulo PQ, it has five distinct solutions.
Okay.
So these are the solutions R1, R2 up to R5. And then when I reduce to mod P, then by using the theorem, I know that this equation have at most two solutions. So those two solutions are S1 and S2.
Oh, so instead of PQ, only mod P.
Right, only
Okay.
mod P when you are doing.
At most two solutions.
Right.
But at the first line, the degree of the equation is also 2. Why we have 5 different solutions? Oh, because it's module PQ. It could be more solutions, right?
Yes, yes, it is mod PQ. It is not a prime, right? So that theorem will not directly applicable here.
Oh, okay. So PQ is not a prime because it is PQ.
Yes,
It's a
product of two primes.
multiplication.
So it is a composite number.
But P is a prime, so that's
Right.
why we can say only 2 solutions
Right.
exactly. Okay.
Yes.
And then you're saying, so S1 and S2, they have a relation with R1 to
R5.
R5.
Yes. So the
And the
thing is, what you saw
relation,
is this
mhm,
R1 to R5. So these are also solutions to this equation, right?
I guess, yeah.
Yes, because this is the thing, right? Because PQ divides this one. So this implies that P also should divide this one, right? So
Right.
that's why R1 to R5, these are also solutions to this one. So when I
So
reduce,
S1,
yes,
S2,
yes, yes,
S1, S2 is within R1 to R5.
yes, yes. So that is there. That will be also there. Also, whenever I reduce, so these are incongruent solutions in mod PQ. So PQ is a larger number, right?
Uh-huh.
When I reduce the solutions to mod P, it will be a smaller set, right?
Small set, yeah.
So that is what you saw, right? So these are the sets in mod 15, but when I reduce to mod 3, it becomes only 1 and 2.
Okay.
Yes, that is the idea. So when I take modulo P, reduce this to modulo P, then it will be either S1 or it will be S2. So that is what I'm saying.
Right, right. And what the relation between S and R is that each of R must be congruent to S1.
Right. Either
Congruent module P.
right, either to S1 or S2.
I see, I see, I see, I see. So you don't know which one, but any R could be congruent module P to any S.
Right.
And then you're saying at least 3 R's
Right. Must go to
are
the same.
congruent to S1
Right.
or S2.
Yes, yes.
I mean, why did you say 2 and 3? I mean, you separate according to the pitch hole principle. You separated between 2 and 3.
Yes, yes. So no, so exactly we are not separating into 2 and 3. I am saying that at least 3 of them will be equal. Means will be same. Either S1 or S2.
But why 3? Why not 2?
No, no. I am saying that so since there are only two boxes and we have five
Okay.
objects, so at least one box will have greater than equals to three elements, right?
I mean, if you're saying it randomly distributed or
Yes, I randomly distribute it. So if I randomly distribute the objects, so what will be the partition? It can be either 0, 5, or it can be 1, 4, or it can be 2,
right?
3, right?
Mm-hmm.
And then 3, 2 again. So then any one of the box will contain at least three elements, right? Or three objects.
Oh, you're saying in any random distribution,
Yes.
any box could have at least 3 elements.
No, yes, at least means one of the box will have at least three elements. That I'm saying. Out of two boxes,
Right. Right. Okay,
uh,
okay, okay.
yes. So I'm taking that box. So at least three of the RIs will be same in modulo P. That will be same congruence, right?
Mm-hmm.
So now we can rearrange them and assume that. So relabeling the objects, we may assume that R1 is same to as R2 is same as R3. in modulo P. Suppose these three are equal. So that we can just relabel, right? Fine.
Yeah.
Okay. So now we do the same thing for mod Q. So same idea. So next, reducing to mod Q. We know that x square minus a congruent to 0 mod Q. This has at most two solutions because Q is
Right.
prime.
Okay. Yeah. Same thing as P. Two
Right.
solutions.
So suppose there is T1 and T2.
Okay.
So now, so same idea. So all the three RIs. So this particular three RI. Now I will take not all five RIs. Now I will consider to these three RIs. So R1, R2, and R3, and look into it in modulo Q. Modulo Q. So this will go to either T1 and T2, right?
But R1, R2, R3. But we have five solutions.
Yes, we have five solutions, but now we are only focusing on these three solutions that are equal in modulo P.
Equal in modulo P. Okay.
So now we have three elements and we have two boxes. Now using the same principle, I can say that at least two of them will go to the same box, right?
Right.
So yes, without loss of generality, we can assume that
You're saying each box will have at least two?
yes, not each box. At least one of them will go to, means at least two of them will go to one box, right?
Right. At least any of the boxes will have two.
Right. So suppose R1 and R2 goes to the same box. So that is R1 and R2 are same in modulo Q, right?
Mm-hmm.
So then what I get? So I get that two things I get. So from the first condition I get that R1 and R2 are same in modulo P, and the second condition I get that R1 and R2 are same in modulo Q as well,
Mm-hmm.
right? But then what does it say? So since PQ and P and Q are prime, so we can combine them, right? So I can get that R1 is congruent to R2 in modulo PQ, right? Can you say that?
You can multiply them. I mean, R1 is equivalent to R2 only when P is prime.
Yes, modulo P. P is prime.
But that doesn't work when P is not prime.
No, here P and Q are prime, right? So this we know.
Yeah, PQ are not prime. It's not the prime PQ.
No, P
Only
and Q are
P.
prime, right?
No, I mean,
Individually,
if you multiply them, it's not the prime anymore.
yes, that is fine. But individually P and Q are prime, right?
Right.
But I am asking that is it possible that if this congruence and this congruence hold, can from these two together, can I imply this one is true?
I wouldn't say so.
So that is actually true, right? Because what does it say? It says that P divides R1 minus R2, right?
Right.
Okay, let me write down. So R1 minus R2 equals to some P times K, right?
Okay.
Now I know that Q also divides R1 minus R2, right? But
Mhm.
R1 minus R2 is P times some K, right? So since
Mhm.
P and Q are distinct primes, so Q has to divide K only, right? Q cannot divide P.
Right.
So K equals to some Q times some R, right?
Mhm.
So then I can originally combine these two and say that R1 minus R2 equals to P times. Now K we can write as Q times R. So it is PQ times R.
Mhm.
So I get that PQ must divide R1 minus R2.
PQ divide R1 minus R2. Okay. Okay.
Right.
Yeah.
So
I see.
now so I got that R1 and R2 are same in modulo PQ, right?
Okay.
So then what is the contradiction? So let us go up where we started. So here we started with that this R1, R2 up to R5. So these are five distinct solutions. Distinct means they are not congruent to each other in modulo PQ.
Right. They are not equivalent, right?
Right. But here actually we prove that they are equivalent. Two of them are equivalent. So this is a contradiction.
Right.
So what
So
we
they
get
are
is
equivalent mode PQ. It's the same
yes,
thing, right?
yes, yes. So thus R1 and R2 are congruent in mod PQ. So contradicting the assumption
Right.
that they are distinct.
Mhm.
So the thing is, so there cannot be five solutions. So this implies the maximum number of solutions is four.
So why we started with five solutions?
Yes, I will explain 1 minute. Right. Yes. So the thing is, yes. So our claim, so they are asking here is what is the maximum number of solutions, right?
Yeah.
So what is the
Okay.
maximum possible solution to this congruence? This is what they are asking. So our claim was that the maximum number of solutions is four.
Okay.
Yes. So that is so you want to prove it by contradiction. So we assume that there are five solutions, five distinct solutions. That is, they are not congruent to each other in modulo PQ, and we proved that it fails. So there are
Oh,
at most the number of solutions will be four, and also we saw an example. So where this four such solution exist actually. So that also we saw.
but why did we get to four because of the previous example?
Yes, yes. This example. You can take any example. So I just chose two primes that are small. 3 and 5 is the smallest odd primes. That's why.
Mhm. Okay.
Right?
Okay. Okay.
Okay.